Hello, I'm Dr. Ben Britton. This is the 5th lecture in the overview of Focused Ion Beam, or FIB, microscopy. In this lecture we're going to discuss FIB machining, lift-outs, and the beginning of 3D analysis. This slide deck was produced with significant support that I want to acknowledge from folks at the University of British Columbia, Imperial College London, Rouen, and with Tescan. So the question is, with the focused ion beam instrument, why do we want to perform machining? Well, ultimately, we'd like to cut shapes and objects through sculpting the surface. We're going to use the system to cut out and extract different objects, and we're just going to be clever about how we present the surface of the sample and how we move the beam across the surface to sputter and yield material out. The cleverness effectively is going to require us to think carefully about how redeposition works, how surface damage, and if we want to look at the free surfaces that are created, to clean them up. And this is to reduce FIB damage and FIB artifacts. Machining itself is useful for a whole range of activities, and we've seen a few of these examples presented so far. Some of these can be micromechanical testing objects, so micropillars, cantilevers and other objects. We can also produce transmission electron microscopy, or TEM lamella. We can also produce site-specific atom probe tomography needles, CT needles and other such. And we can also do site-specific analytical electron microscopy or scanning electron microscopy for tomography, and also TEM tomography needles again as well. So here are some examples. In this example, we could, for instance, make a micromechanical test specimen. So this is a micropillar. We've actually seen this as deformed in a previous lecture in this series. We can also sharpen an indenter tip, and so we can make a sharp nanoindenter by effectively cutting and leaving a very sharp pillar on a pedestal in there. We can also use other mechanical geometries. So this is a cantilever where we have a thin film and we use a wedge to deflect and bend that cantilever object. Or we can do effectively a micro-tensile specimen where we can pull apart a tensile specimen by having a fibbed gripper and the surface of the material with the tensile specimen cut into it. To do a lot of these processes and to enable us to do lift-out, we could use effectively a micromanipulator needle. And so this needle effectively is located on like an XYZ or an XYZR stage. This is one such example. And in this process, we effectively have the sharp needle, and we can stick the surface of our object through welding with the gas injection system, and we can do that to enable us to put the needle in the surface of the sample, and then we can move the needle upwards or move the sample downwards and liberate the object once it's welded. If we've got an R rotation stage, such as on one of the Omniprobe systems, you can effectively rotate the object, and this can enable you to access and look at how the shape of the object is in 3 dimensions. So many FIB instruments include a nano or micromanipulator needle. Typically this is a sharp metal rod. It's often actually the end of this rod is a consumable that you might change, and you might also sharpen to improve the sharpness to enable you to be even more site-specific. It's attached to a very fine precision movement stage, typically nanometer or 50 nanometer encoded. And some examples will be XYZ allowable, and some will have rotation about the axis of the needle, so an XYZR, which enables you to rotate the sample like this. The specific mounting position of this manipulator underneath the instrument and where it is with regards to the SEM and FIB columns will impact the use. And we just recognize that these needles are consumable. It depends on the particular setup, but they can be maybe $100 or more per needle depending on which ones you're using. And we'll also typically, depending on what we're doing, we might sharpen or control the end effector of that needle in practice. So if we want to do preparation of lamella for transmission electron microscopy. Let's just have a look at that process. So site-specific lift-out enables us to pick a particular region in our object and prepare an electron transparent sample. To do this, we will effectively put a protection layer on the surface. Above this layer, we'll then cut out a sample. It can be wedge-like or parallel-faced. We'll attach it to our lift-out probe or needle, and that sample will then contain the features in this cross-section. We'll then effectively stick this very small, it's often say 5 micrometers by 5 micrometers in size. We'll then attach this on a mount or grid that can be effectively manipulated by like a pair of tweezers or similar, typically vacuum tweezers these days. And effectively, once it's been transferred onto the carrier sample, we can then perhaps thin the sample or perform subsequent analysis. So the goal is to produce a site-specific lift-out. We want to extract the sample with minimum damage of the sample, especially at the last thinning layers. And we're going to attach this to a carrier that can be manipulated. For instance, it can sit on a different part in the microscope, or we can use this to transfer from one instrument to another to move this, for instance, into a TEM. So this is an example of a prepared lamella that was kindly prepared by colleagues in Tescan. And so this lamella effectively is now cut out. It was cut out from either side, so we've got trenches either side. We've got a platinum coating on the top layer. And then the sample was effectively extracted and then welded on the side of a copper grid. The grid is over here. The lamella is sitting here, and then it was thinned. So we've got the platinum cap that's been reduced after the thinning process, and this sample is probably less than 100 nanometers in thickness. What's super nice is you can see there's a grain boundary and a series of precipitates, and this is just showing us in the SEM under the ET detector. And we'll see that we can do improved analysis by using, say, a STEM detector or moving it into a TEM. So to perform a lamella preparation route, traditionally what we will do is we'll effectively have a target region that we will effectively cap the top surface of this object, and then we perform side trenches where we'll gradually polish in to leave us the target and some thickness either side. We've gone down the trenches on either side, and this is looking at in the SEM, and we'll do a series of staircase cuts as presented here, and these are the E-beam and I-beam caps that were prepared on the top of the surface. In the SEM, we can see at the side angle, we can see effectively we've now got this thin wall that's liberated, and in the FIB we're looking down the top, and this is under the plasma FIB. We can see that we've now got effectively those cuts. We can see the cap layer. What we'll then do is effectively we'll undercut, so we'll cut under here, so we can tilt the sample in the FIB to enable us to cut underneath and to cut up here, and we'll bring in a manipulator in to weld. We'll liberate the foil. We'll bring it off the surface and then weld it. So we can see this process where we've now effectively done the trenching either side and we've capped it. We've then polished away that free surface either side, and then we do the undercut process to enable us to have it that this can be a freestanding lamella. We then can take our nano manipulator and we can effectively perform a small bit of deposition to weld the end of our manipulated needle onto the end of this. And then effectively it's been undercut, and then we can effectively cut off the cut off the lamella. So now this lamella is simply attached to the nanomanipulator. We can then pull the nanomanipulator upwards with regards to the surface to liberate it, move the sample out the way, and effectively bring it and attach it to a half grid. We'll weld it onto the half grid, and then we'll cut it off the needle as presented here. Once we've mounted it on the grid, we can then perform effectively thinning. So the thinning enables us to get it to electron transparency, but also enables us to remove the damage that was presented from when we did the FIB work, because a lot of the FIB work will have been done effectively at very high probe currents and voltages to enable us to cut up material quickly. So we can now see that we now have a very thin section of this sample. This is the electron transparent region that we're going to be interested in. And then we can image, and this is I think about a 5 micron by 5 micron region with a tungsten cap that's presented on this particular sample. And when we image this at 10 and 5 kV, we can start to use two different voltages to establish whether this sample is interesting. And so effectively whether the sample is sufficiently thin to reveal contrast. And you can just about see the presence of contrast, which is the different effectively bainitic or ferrite-like laths within this material. To do this in practice, this is showing us the different steps. So we start off with a protection of the initial cap layer with an electron beam deposition. This whole lift out was produced on a xenon FIB in this particular example. And so here we effectively now put the electron beam deposition. We're going to do an ion beam deposition. We're then going to trench. We're going to roughly polish to give us the thin lamella. We're then going to do the undercut, the J cuts in here. And then we go through the process, and effectively we're now going to have it that we've undercut. We're then going to attach the manipulator needle. We're going to cut the lamella free. We're going to lift out the object. We're going to insert the half grid. So in our particular system, we have to break vacuum, put this sample in, and then effectively do the lift out. You don't have to in all systems. And then we can attach the lamella to the half grid. And then we can cut the needle free, so the sample is now attached to the half grid, and then we can do the thinning and full thinning of this. So that's the steps with conditions that we used for this steel sample. And here are the steps shown in pictorial form. So the E-beam, I-beam cap, trenching, polishing, then effectively this is the polishing at 0 tilt. We then bring the needle in, we do the welding process, we then can do the J-cuts in this case. We can then cut it free in this case, and then we're going to effectively move this lamella upwards so it's out of focus, the sample remains in focus, and then we're going to move this sample out the way, bring the sample towards the grid, and then we can weld it onto the grid itself. We can then, once it's been nicely welded, we can cut it free, and then this is the sample as stuck on here. At this point we might want to put some more deposition just to secure it a bit more. And then we can effectively polish to give us the electron transparent window. Here we can basically also have reinforcement, so we see that we haven't thinned it fully, and that can be useful to try and reduce the influence of residual stress and bending in the thin lamella that's formed. And you can see this is the 10 kV and then this is the 5 kV imaging that's presented here. This is just showing us those steps now looking instead from the SEM column. This is now looking using the plasma FIB column. And so here we can see those sort of steps as we go through the system. Again, remember that the plasma FIB has less good resolution for this amber X1 or X edition. And so we can see the sample. But the ion beam does give you nice contrast of the different grains as presented. We can see the welding process is sticking. We can then see that we've lifted this out the way. The sample no longer is located, sorry, the lamella is no longer located in the sample, it's on the end of the needle, and then the needle is brought towards the copper post, and then it's welded into place. You can see this is the back weld that's presented, and then we do the thinning process as we saw beforehand. In this particular example, we were doing the technique called transmission Kikuchi diffraction. This is basically an EBSD-like method where we can use that to measure the crystallographic orientations and microstructure. So these are the orientations as presented in the phase, and we can look across this structure. This is at very high spatial resolution. Remember that this foil is about 5 micrometers across, and so this was super nice. This is a 2.5 micron scale bar. We can reveal that microstructure with very high precision in here. We can also do more traditional STEM imaging, so we have a STEM in SEM detector on side our Amber X instrument, so you can do bright field, dark field and HADAF to reveal the different microstructural regions as presented in here. Importantly, the bright field, dark field and HADAF are located or with respect to the through thickness attenuation and scattering contrast. The TKD data is from the bottom surface of the foil. So we have to be in, it's typically the very near surface, and so that's where the final polishing steps at low kV are very important in this example. So when we see this, and this is a different example that was prepared kindly by colleagues in Tescan, in here we can see effectively that the polishing steps are really nice because careful polishing goes from effectively the attachment step Once you do the polishing nicely, you can get a beautiful example where you see that grain boundary and all the precipitate starting to appear. And here we've effectively gone from 30 kV polishing to a low kV polishing in this example. Now, one of the questions that lots of people ask is then how do you determine the thickness of your sample once you've prepared it? There are a few different methods. This is a method by Conlon et al., where effectively we can look at the relative contrast from a through the lens detector, which is effectively located in the SEM pulp piece, and we can have effectively an ion type and secondary electron detector. And we can see here that they've done a stepwise based thickness of different regions in this particular piece of silicon. So you have a thin section to a thick section. And then they've linked this for a T over lambda EELS measurement, which is one of the classical methods for thickness. This enables you to extract the inelastic mean free path from the T over lambda. And what you can see effectively is that you can get some nice, effectively grayscale values matching with the thickness from T over lambda. And if you well calibrate this, you could then use this as a method for you to do an EELS-free calibration of the thickness of your foil, which can be particularly powerful as you want to increase the throughput of your analysis method. Other methods that you can use, and this is there's a description of this on the TestScan website that talks about lamella preparation, and you can effectively exploit the electron transparency and contrast. So effectively, the thickness can be estimated from the change in lamellar color. You use the ETD detector and the sample goes bright when the sample is sufficiently thin. When you then play with the voltage changes the interaction of the secondary and backscatter electron depths. And so effectively this thinness, as we see here, we change from a 5 kV to 3 kV. We can see effectively that this scale is changing quite significantly. And that enables us to estimate that when the contribution of backscatter starts to decrease, that tells us, or the contribution of backscatter very significantly, that can tell us about the thickness of the foil to give us a good estimate of this thickness that could be calibrated via other methods. We can also, of course, image using a 30 kV stem detector to see whether the contrast that we're interested in starts to appear nicely. So we can also bear in mind that the polishing steps, as we do this, we have to be very careful to appreciate about the consequences of FIB damage. So recall that we have the sample that we care about is this very thin. Typically it'll be less than 100 nanometers of the total foil thickness, but now we might have a surface layer, and if we're 30 kV, we could have a 100 nanometer thick foil that has 20 nanometers on either side of damage, because we haven't polished or developed a strategy properly. If we get this to be down to 1 kV with gallium, we can get now something like a 1.5 nanometer, which then gives you like a 4% if this was 100 nanometers thick. 4 nanometers or so would be damaged, 2 nanometers on either side, so 4% of this. Now, this would be using a gallium probe for this. You can also use some other methods, and so one of the exciting aspects that we're getting at UBC is effectively the Aura gentle ion beam system, and so our Amber 2 gallium FIB will be equipped with a gallium probe, focused ion beam, but also a broad ion beam that has effectively an argon ion system. And this is highly integrated to enable us to have lift-out polishing and stem in SEM without breaking vacuum. So this is the system as shown from the promotional materials from TestScan, but effectively we have the electron column, we have the gallium column, we have a manipulator needle, I think is this one, and then the GIS system. And then we have the Aura system that enables us to effectively open this aperture and insert an argon ion plasma, and that enables us to effectively polish our material to remove layers in a glancing angle, and we can use the stage to sweep the sample to reduce so-called curtaining artifacts associated. What's really cool here is that we can now remove more and more of that surface damage layer, and we can polish down to say a 200 electron volt thickness with an argon ion. So that's effectively, remember that the argon ions have a very short stopping distance and don't tend to alloy in those systems. And the broad ion beam plus the rocking enables us to reduce the so-called curtaining artifacts. This has some quite significant benefits. This effectively is just an example of a titanium nitride sample that we did on the demo. And in this case, we've now done this with a 2 kV FIB polish. We see the sample, it looks pretty good. There's 2 different phases, there's some stacking faults, 1 micron scale bar, this is stem in SEM. And then post the broad ion beam method, so we did the 500 electron volt BIB method using the argon, and we see that we now get a significantly improved, much higher contrast in the features that are presented, and that's much more easy to interpret. So that's a nice aspect where we can combine the FIB with final polishing steps. Other final polishing steps could involve using an ex situ broad ion beam, or we could use things like flash polishing that are described in the literature. Now, FIB lift-out doesn't have to be done always in cross-section. We can also do a so-called plan view, and this can be particularly useful when you want to look at the surface of a particular component, or for instance, a grown structure. So you can do a deposition, and effectively you can deposit on the top layer, and then what you do is you basically produce a very thin section out of this material. You attach it to your needle, and then you attach it, and you could use, for instance, the manipulator to then bring it, and here we've put the grid, the Omniprobe grid, now on the side of a stub. So then we can effectively side weld that grid on the side of the stub, and then we can effectively polish to remove the material and get it to be super thin to enable us to have a plan view rather than cross-section of our object in there. In addition to doing this stuff all at room temperature, we recognize that there are certain reasons why we might want to perform our preparation using a cryo focused ion beam. Some of the simpler cryo systems effectively have a cryo stage, where we can now have the cryo stage that has cooling, typically through, for instance, flowed liquid nitrogen, to enable you to cool this stage downwards and cool the sample. When we do this, we want to reduce effectively condensation on the sample, so we tend to also include an anti-contaminator system, and we might also do some clever tricks with the micromanipulator as well as the gas injector systems. We'll see this some important details in a short moment, that there are challenges when you're using cryo, specifically with regards to the gas injection system, because effectively you can get condensation of the gas all the way across the surface of your sample. You can also get condensation of, say, water on the surface of your sample and frosting, and so the anti-contamination system is important to reduce water and ice of this. One of the other pieces is that one of the bits that you might have to think about is, do you need to do the final transfer out of the system cold? This will depend. Some of this is important. Biological systems that are plunge freezed, etc. Yes, you need cryo transfer. Other systems you may just care about doing the FIB work at cryogenic temperatures. So we can do cryogenic transfer by effectively enhancing the complexity of the system. Now effectively we have effectively a cryogenic transfer system that enables us to have the cooling systems, anti-contaminators, cooling of a variety of bits and pieces around the column, but we can also effectively have a cryo rotation stage on a long arm that enables us to take the sample in and out and bring it via a loading system. And so this is the overall system where you can now have an arm that's attached to the side of this, and this can be particularly important for things like battery materials, where you might not want to have the electrolyte or the such doing various things. One of the challenges, however, at cryogenic temperatures was noting that effectively if you do trying to do cryogenic deposition, you get condensation of the organic precursor across the sample, and so you get this mess on top of your piece. Now there are a few different ways that people solve this. One example is a suggestion, and this is very emerging, but effectively use of a different cryogenic gas or gas for this. And in this example, it's the use of propane, as suggested by Pereira et al. In here. And so that Pereira et al. Lets you have a targeted deposition. This was done at minus 165 degrees C. And now you can effectively use this to cryo weld and attach in a very similar way that we were doing the room temperature work. Other methods, as suggested by colleagues in Imperial College London, is the use of adhesives, SEM glue, to enable you to effectively attach the sample using this sort of glue structure to enable you to do the manipulation with posts for lift out, etc. in there. If we're moving beyond cryogenic, we don't have to do the full lamellar lift out in the microscope. We could do the liberation of the foil, And then we can effectively use a manipulator needle to enable you to use, for instance, van der Waals forces or similar to lift up and deposit the sample on grids, on MEMS chips, or effectively on copper grids where you could have a hole for electron transparency. The attractive nature of this is that you're not tying up the microscope with that expensive operation, so you can significantly improve throughput of your system. And there are some very sophisticated ex situ lift out hardware now on the market for this. Other aspects is that ex situ lift out can reduce the damage to the foil, and so that can be quite attractive for certain systems. And so here's a series of examples that are presented. One of the other bits you can do is you can be clever about how you do the thinning. And so what you might want to do is, for instance, prepare a significant extent of wall of your structure, and then you can cut out a series of electron transparent windows at different thicknesses through your object. And that can be particularly useful if you want to look at sort of a layered structure, or you want to manage things like effectively residual stress or other such, or have multiple samples, where you could, for instance, use a wedge-based macroscopic polish to produce the wedge, and then use the FIB just to make the localized, very thin, constant thickness cross-sections. And so that wedge polishing is done with a tripod polish or broad ion beam machining with cross-section, and then you use the FIB to selectively thin the lamella from that region. It's not as site-specific because, of course, the sites are all located on the edge of the object, but you can get significant throughput enhancements with this. Moving beyond TEM lamella prep, we can also use atom probe tomography. Those of you unfamiliar, I suggest there are many other sources for how APT works, but broadly speaking, we produce a sharp needle and we evaporate that surface atoms in a control ions in a controlled manner in a very expensive but very useful atom probe tomography instrument. One of the growths of this area is to use this to do site-specific work, but in addition to site-specific work, you can also do things like look at insulator samples that can be difficult to repair using other methods. So one of the major methods that this is done, and I'm now borrowing a lot of the slides that were kindly shared to me by Baptiste Goult, and in this particular setup you can basically produce a long cantilever, and that cantilever can then be used to chop off the end of the cantilever and deposit on a pre-prepared post. So the sample, effectively you produce the cantilever, you then attach it to the needle, and then you chop off the edge of the Toblerone, and this can get you multiple samples from this linear object, so your throughput can be very high. So we're going to use the gas injection system to do a protective layer and to attach it for each of the welding operations, and effectively this will enable us to get this. And once we've done the weld, we can slice it off the wedge, move this Toblerone to the next microtip post and prepare a new sample, which is wonderful. So we can also do this in a site-specific manner. So this is some stuff that I was involved in, courtesy of Isabelle Newton, looking at zirconium hydrides, where we have a series of site-specific analysis where we wanted to look at hydride metal interfaces. So we did site-specific work by producing fiducial markers, put a protective layer. We then prepared a Toblerone type region with controlled understanding of the area that we want to look at with markers. We then produced effectively the Toblerone, we lifted out this Toblerone, put it on the end of a manipulator, brought this towards a post, we then effectively take this Toblerone on top of the post, we then cut off a section to enable us to have a freestanding object, and then we do a series of annulus mills where we kind of use a donut-like polish to sharpen this down to a very sharp point with a typical radius that's less than 200 nanometers. And we'd like a reasonable aspect ratio so we can get a fair amount of distance evaporated. If the needle is too sharp though, you can get some issues where the atom probe needle may crack when it's being evaporated using, say, voltage pulsing or laser-based methods. But this is super powerful, so this is just showing this example where we did site-specific work, where we picked a series of different hydride metal interfaces, and we looked at a series of different hydride types in this particular work. This enabled us to do some really cool bits and pieces to start to look at effectively the decoration of iron and tin associated with hydride metal interfaces. And we did this specifically starting to look at different isotopes of hydride that were presented in this work. What became quite apparent is that effectively the hydrides that are presented, you actually get significant hydride formation due to the influx of hydrogen in the FIB prep. And so this motivates effectively the use of cryogenic methods that can reduce that approach. Cryogenic methods in this case are relatively similar to what was done beforehand, except the whole system is kept cold to enable this to work. And there's some details that are important for how the manipulator and effectively the process has worked. One of the major bits here is that the welding process has to be changed, and so if we're doing cryo-FIB work, we might use an alternative welding strategy. The alternative welding strategy in this case is with a small object, you can basically do a series of line cuts in the object, and when you do the line cuts, the redeposition enables you to lock the two materials together. And so these are the line cuts that are presented in the object to enable you to weld this. So you do the repeat line cuts, and then more cuts to put in this, and then you get metal and there's posts reattaching to lock these two together. And that can be very useful, so that avoids you having to use the GIS to enable this deposition, so you can do it at cryogenic temperatures in here. The full description of this can be found in the paper by Eric Woods for this, and this is done for an icy sample in this case. The article is currently under review, but there's an archive preprint. So hopefully I've persuaded you in this module that the FIB machining, it's a versatile nanoscalpel. We can effectively remove regions relatively easily, and we can construct a series of three-dimensional objects using negative 3D printing to cut away and create and sculpt artifacts, and specifically for sample prep. In this process, we're going to be very careful with redeposition and ion damage, and we're going to manipulate the samples to hold to grids via manipulators to enable us to have macroscopic objects that are relatively easy to manage outside of the microscope and move between different apparatus. This will lead us into module lecture 6, where we'll look at 3D FIB tomography and analysis in our next lecture.